I'm going to now record the first part of the lecture on Chapter 7, Alkene Structure and Reactivity. And we're going to start with just some fundamental concepts about alkenes. They're also called olefins, and the reason for that is because of their smell, and this got the same root as the word olfactory. And so when you say you smell Texas City, that's what you're actually doing, is you're smelling that sharp smell of alkenes. They are found naturally also. They're obviously made commercially, and they have a lot of commercial uses, some of which are covered in these next couple of chapters. All of these molecules will have at least one carbon-carbon double bond, and this will provide a point of access into the carbon skeleton where you can get other reactions to occur. The trends in the boiling points and melting points and so forth are similar to alkanes, so it follows approximately the molecular weight, and then if it's branchy, then it will have less ability to get close together, and so the branchy molecules will have lower melting points and boiling points than the straighter chains. But when you have a double bond, because of the p orbitals overlap, that restricts the amount of rotation you can have right at the double bond, because those p orbitals have to stay lined up. And so that means that you can have geometric isomers in alkenes, which is a subset of stereoisomers. So we're going to talk first about points of unsaturation. This is a term that the book may call degrees of unsaturation, but I use the term points of unsaturation so that it's not confusing with degrees of carbon. And we're going to use the alkane formula as our reference. So CnH2n plus 2 is the maximum number of hydrogens that a given n number of carbons could possibly have, based on the idea that they need 4 bonds. And we've kind of looked at this a little bit already when we talked about making rings. You have to have an extra place for another carbon-carbon bond, so you would have to lose a hydrogen off of either end carbon to make a ring. And so that is actually one point of unsaturation. 2 hydrogens are lost for every time you make a ring, a double bond, or if you want to make a triple bond, it's going to take 2 hydrogens per double bond, or a total of 4 hydrogens, so that is equal to 2 points of unsaturation. And once you get this idea, then you can look at a formula and you can tell what kinds of structures are conceivable. And also, if any one structure that you come up with that meets the formula has a double bond or a ring in it, then all of them with the same formula are going to have 1 point of unsaturation, either a ring or a double bond. And also, when we talk about points of unsaturation, this is an indication that the level of oxidation of the carbon has changed because you've lost hydrogen. So a carbon system that has points of unsaturation in it is in a more oxidized state than the alkane. And so these things are all fitting into the idea that we understand the basic concepts of what makes sensible organic structures. Now, in order to determine points of unsaturation, sometimes we have formulas that have other atoms in them. And anything other than hydrogen or carbon, we're going to call those heteroatoms. So let's talk first about oxygen as an example of a heteroatom. And you can figure this out, if you can't remember, by just using really simple molecules. So if you have the formula C2H6O, then you could either put the oxygen in between the carbon and the hydrogen, or you could put it between the 2 carbons. But because oxygen needs 2 bonds, it's not like you need to add or take away any hydrogen. In other words, you can pretty much ignore the oxygen when you figure out points of unsaturation. You just pretend like it's not there, and it won't affect anything, even if you have a double bond. So here's another example, C2H4O. Well, I could draw a double bond between the 2 carbons, or I can draw a double bond between a carbon and an oxygen, but again, that's 1 point of unsaturation, and the presence of the oxygen isn't affecting the number of hydrogens. So if I subtract the C2H4 from the alkane formula, ignoring the oxygen, I get a difference of 2 hydrogens, and there's 2 hydrogens for each point of unsaturation, so that means there's 1 point of unsaturation, which we're seeing with either of these structures that have a double bond in it. And one other thing that I could do with 1 point of unsaturation is draw a ring, and you can actually have a 3-membered ring where the oxygen is 1 member of the ring and the 2 carbons. That's another valid structure for that formula. If you have heteroatoms that are halogens, you could have to, again, think about the simplest case. It's not going to really affect the points of unsaturation, but in order for us to figure out that, we need to think about the fact that when you put in a halogen, you have to replace it a hydrogen. And so in order to determine points of unsaturation, we're going to put back 1 hydrogen for every halogen that we have in the formula. And then we'll figure it out. So this symbol, these little 3 lines, that means is equivalent to. So this formula, C2H5Cl, is equivalent to adding back 1 hydrogen for this chlorine. The equivalent is C2H6, which is the alkane formula, so there are no points of unsaturation in that formula. If we do the same thing with 2 chlorines, we have to put 2 hydrogens back. Again, that's still no points of unsaturation. In this formula, if we put 1 hydrogen back for this bromine, that's C2H4, and that compared to the alkane formula indicates there's 1 point of unsaturation, and here's an example of a structure that would fit that formula. Another case that we'll run into pretty often are nitrogens as the heteroatom. And when you think about it, nitrogen has to have 3 bonds. So that means that every time you put in a nitrogen, you need an extra hydrogen. It's kind of like the oxygen. Again, if we go back to look at simple cases, let's look at this formula. So if you put the nitrogen in between the carbon and the hydrogen, you still need another hydrogen to satisfy the 3 bond requirement for the nitrogen. Or you can put the nitrogen in between the 2 carbons, but again, it needs that extra bond. So when we look at the formula, we're going to take away 1 hydrogen for each nitrogen. So this formula is going to be the equivalent to C2H6, which again is the alkane formula, no points of unsaturation. If we have this formula, we take away 1 of these hydrogens for that nitrogen. That's equivalent to C2H2, which would be, here's an example of a formula that would meet that. This is a common functional group, a nitrile. And you notice that even though it has a triple bond in there and a nitrogen, we still have that odd number of hydrogens because of the presence of the nitrogen. So this is 2 points of unsaturation. Here's another structure I could draw for that. And if we look at the math, here's the difference, 2 points of unsaturation. So here's some example problems to look at. So here's a set of different formula, and you could calculate how many points of unsaturation are in each. And so how do you start? Well, you've got to get it to the equivalent structure or decide if you can just use what you have there. So if we start with this formula up here, we see there are halogens. We know that we have to add back a hydrogen for each halogen. And so we're going to adjust that formula accordingly, and then we'll compare that to the alkane and so on. So for that one, if we've added back 2 hydrogens, then that gives us the equivalent formula of C5H6. The alkane formula, remember, is Cn, 2n plus 2, so that's 12 hydrogens. The difference is 6. So divided by 2, that's 3 points of unsaturation in that formula. We can ignore the oxygen, so we're going to compare this one to C7H16 is the alkane formula. We have a difference of 4, so that means we have 2 points of unsaturation. For this formula, remember we have to remove 1 hydrogen for each nitrogen, so that's going to be the equivalent of C6H4, which we're going to compare to C6H14. That's a difference of 10 hydrogens, or 5 points of unsaturation. Now that may sound like a lot, but if you think about it, an aromatic, if you go back and look at your table of functional groups, benzene ring is an example of an arene, it has 4 points of unsaturation right there, and that's pretty common that there's a lot of points of unsaturation in any aromatic. Here's a bigger formula. No worries. You just need to take away 2 hydrogens because you have 2 nitrogens, and don't worry about the oxygen. So our equivalent formula is C15H22, and 2 times 15 plus 2 is 32, so we've got a difference of 10, and another example with 5 points of unsaturation. So another thing we might do with this kind of problem, or this kind of information, is we might have a formula that we need to draw structures to go with it. We've had a lot of problems like that already, and this should make it a little easier to do that kind of problem. Now I've added to that part of this problem to try it with a different collection of functional groups if you can. So the first thing you do to start is you need to figure out how many points of unsaturation there are. And so we're going to compare this formula that we have here to the alkane formula for 6 carbons. Ignoring the oxygen, we get a difference of 6 hydrogens, or 3 points of unsaturation. So what can they be? Well, you could have several different possibilities. You can list all those: 3 rings, 3 double bonds, 1 triple bond and 1 double bond, or 1 ring and 2 double bonds, and so on. So those are all the possibilities. But obviously every structure that you draw has to have 3 points of unsaturation. So we can also have carbon-oxygen double bonds, so we're not limited to just carbon-carbon double bonds, and that's why I didn't put that specifically here. This just means some kind of double bond. And so here are some pictures that I came up with, and this is just a few. There's many others that we could draw. And I asked for a variety of functional groups, so then it might be nice to practice and figure out what functional groups we have in here. So see if you can figure out these functional groups. So this guy has in it, this kind of feature right here is an ether, and this is an alcohol. And it turns out this is also an arene, although we haven't studied those yet, so you probably wouldn't recognize that. And it's also cyclic, which doesn't keep it from being an ether. In this one, all right, you've got a carbonyl, and remember, a carbonyl by itself is not definitive. So we look to see what's on either side of the carbonyl, and we have a carbon on both sides of this carbonyl, so that makes it a ketone. This is another carbonyl, but it's got a hydrogen on one side and a carbon on the other. That's an aldehyde, and this is just an alkene. Here we have a carbon-carbon triple bond, and those are called alkynes. We have another ether here, and we have a carbon-carbon double bond, which is an alkene, and we have an alcohol. And lastly, we have alkenes in here, and this feature right here together, again, looking at the carbonyl, next door is an oxygen connected to a carbon. So all of that together is an ester. Alright, so let's talk about alkene nomenclature in general. And the rules are going to change a little bit as we go through the book, looking at the different functional groups. They will affect the way that you name things. And one question is, why do we not just learn how to name everything at once? And the reason for that is because it's easier if you kind of go through it a little bit at a time. But basically the rules of nomenclature are going to follow the oxidation level of the carbon. So alkenes are going to take priority over alkanes because the alkene carbons are in a higher oxidation state, as we discussed earlier. So the double bond is going to be part of the longest chain that you can find. You have to go through the double bond. You can't have one of the carbons of the double bond be part of the longest chain and not the other. They both have to be part of the longest chain that you can find. And we're going to try to give that double bond as small a number as we can, and that will take priority over whatever other things you have hanging off the chain. When we get ready to write it down, we'll again put things in alphabetical order and put the numbers that tell where on the chain it is along with those groups. And for the alkene, because we've already established that the nomenclature has to go through the double bond, then we only need to tell the reader the number for the first carbon of the double bond, because we all understand that the other end of it is be the next number. And we're going to put the alkane parent name in the alkene. The A is going to change to an E inside of the word, and to tell where in the chain it is, you can either put the number in front of the whole word, or you can split it open, and I'll show examples of both of those. And if you have more than one double bond, you can use prefixes for multiple appearances, but you also have to have multiple numbers to tell where they all are. So let's look at some examples. So here's a fairly straightforward case. It's obvious that in order for us to find the longest chain that goes through the double bond, and to give it as small number as possible, we're going to have to start on this side of the chain. And so let's add our numbers in there. So now we see that we have this chlorine on carbon number 3, we have a methyl on carbon number 2, and another one on carbon number 5. So we can add that all together, and so this is an example where you put the number in front of the whole word, but we understand the only thing in this word that needs an indication of where it is the "ene" part of it, so it's pretty clear. If you have a ring, the double bond again has to be numbered through the double bond, and by default it's to give it the lowest number. One end of it's going to be number 1 and the other end is going to be number 2. So then your only decision is, do you go around the ring clockwise or counterclockwise? And to give everybody else as small numbers as possible, that will be how you decide. So if I start on this carbon and go this way, I get these groups at smaller numbers than if I started here and went this way. So I get these groups at 4 and 5, and hopefully you remember what the group name is for this particular 4-carbon group. It's a 4 carbons. The 4 carbons with respect to each other are in a row, and it's attached through the secondary position of the 4 carbons, so that's a sec-butyl group. There's a bromine, so we write that down. And whether you want to use the sec in alphabetization or not, it still comes after the bromo. And so there's this number, and here's an example with the word broken open, and put the number inside the word for the location. Here's a bigger chain. Now if you look at it, if you went all the way around the outside, you could get a longer chain, but because we have to go through the longest chain we can find that goes through the double bonds, we're going to have to go through this way. Now if you go this way, or if you come across here and go around to the bottom, it doesn't matter. The longest chain you can find is 12 that goes through the double bonds. Even though there was a 13 carbon chain that did not go through double bonds, it doesn't matter. We have to go through the double bonds. And to give them as small numbers as possible, we're going to start here, and so we'll add in some numbers. So I went around that way. So that makes this a 6-carbon side chain, which I'm going to call a hexyl group. And that's the only thing that I've got hanging off of here. And so this is a diene. There are 2 double bonds, so I have to tell where they are in the chain. So I can say 6-hexyl, 2,5 for where these double bonds start. And the name for 12 carbons is dodecane. So we're going to open that word up and put the di in front of here. Now we could have also put these numbers right in here in front of the di if we wanted to do that other style of nomenclature. So here's a question for you. Is this molecule clear? Is everything that you could possibly write about this number included in that name? And the answer is no. There's actually a geometry argument that we could add to this name. So we'll come back to that in a second. Some common names that I want you to know for these groups are going to be important for several different reasons. Some of the common names use the -ylene ending. So ethene is the IUPAC name for ethylene is the common name for the 2-carbon alkene. And we talked about 1-butene is called butylene, and the branchy version is isobutylene. And this guy right here doesn't use the ylene, but this isoprene, this is a very common molecule, both biologically as well as industrially, an important feature. And if you've heard of neoprene rubber, it's made out of a polymer. That's a polymer of this stuff. Some other things you might need: this group right here. If you take this as a group, so this thing is attached to something else, and we needed a group name. This is called a vinyl group, or you can call it an ethynyl group. But we're going to also talk about positions. So anytime we talk about hydrogens that are directly attached to the carbon of a double bond, we could call those vinyl hydrogens. Or if we had a chlorine over here attached to this position, we could call that vinyl chloride. If you've ever talked about PVC pipe, that stands for polyvinyl chloride pipe. It's a polymer of that molecule with a chlorine there. Another group name that we will run into in a few more chapters is the allylic position, and that is one carbon away from the double bond. So if I take this as a group, we could call it an allyl group, or I can call this an allylic position. So if I look in this molecule up here, for example, this is the allylic position. It's one carbon away from the double bond. These are vinyl hydrogens. That's the allylic. There's no allylic position here, but I do have 4 vinyl hydrogens, and so on. In this molecule, these are the 2 allylic positions in this molecule. There are no vinyl hydrogens at this end, but I have 2 vinyl hydrogens there. And this particular situation, I can't number the chain starting at one end of the double bond and going through the double bond. I can't go on around the ring. So the way we deal with that is we think of this as a cyclohexane ring, and we add the term methylene, which is short for a carbon double bonded to the ring. A CH2 group is sometimes called a methylene group. So this is methylene cyclohexane. And you'll have that situation only happening on rings. Alright, so now let's talk about the geometric isomers. We know that alkenes can have isomers just like rings, so you could have 2 groups on either the same side or opposite sides of the double bond. And if you have that information given in a name, then you have to include it in your drawing. And if people give you that name, you would draw the right thing. It might be pretty straightforward if your double bond only has 2 groups on it, 2 chunks of carbon and 2 hydrogens. So we had this earlier example, and so if you look at it, there's 2 double bonds in here. This double bond has the same chunk of carbon on both sides of this carbon. So there's no geometry argument here on this double bond, because you could say, well, this chunk of carbon is either cis or trans to the same stuff. So there's no problem. But now look at this one. I have this methyl group, and it's on the opposite side of this double bond than this chunk of carbon. So now I do need to talk about the geometry of that one. So it's drawn as trans, and so if I put a trans out here in front, then that's a better name for that molecule. And anytime you have a double bond either at the end of a chain, or if it's got the same things on the same carbon end of the double bond, you don't have to worry about it, but otherwise you do. Now here's a different case. So this situation, I have 3 different things on my carbon-carbon double bond, and the 2 things that are the same thing are not on the same carbon as in the previous case. So if you have 3 different things where the repeating group is on different carbons, you can't use cis trans. Or if you have 4 different things, you can't use cis trans. And remember what we mean when we talk about 4 different things. It doesn't necessarily mean just carbon. You may have to look a little bit further to see if they're truly the same things. And we talked about that earlier in the last couple chapters ago. We talked about the Conning-Gold-Prelog rules for determining priorities. We're going to use those again to determine the priorities around the double bond. And we have to do that because if we said this was cis, we wouldn't know for sure if we were talking about the methyls or whether we were talking about the chlorine and the ethyl. So you could be talking about molecular weights, or you could be talking about the same size things. It's just not at all clear. And remember, we want the nomenclature to give another person the ability to draw without any level of confusion the right structure. So let's see how we can apply these rules to this situation. We're going to think of the carbon-carbon double bond as a unit. So it's like you grab that in your hand and then you look to see what's attached immediately to each one of those carbons. So there'll be 4 things out there to look at. And so we're going to determine the priorities. Remember that it's the higher the atomic number, the higher the priority. And then if there's a tie, then you look at the very next atom and so forth. And you don't go any further than you need to break the tie. And once you have all those priorities established, then you look at each carbon separately. So first you treat it as a unit, then you treat them separately. And so on each carbon you determine the higher priority number, and we'll call the lowest number is the highest priority. We'll label that as high, and if you get a larger number, then that's lower in priority. We'll label it as low, and we'll go to the other end and we'll do the same thing. So here's what I'm talking about. Suppose that we've established our priorities around this molecule, and so we come up with these priority designations. So if we look at this carbon of this double bond, in other words, we're going to now divide it in half and look on this carbon. Well, 1 is higher in priority than 2, so we'll label that one as high and this one is low. Now we look at this end, 3 is higher than 4, and so we'll label it accordingly. And the designation that we're going to use is the high things are on opposite sides, so that's kind of like trans. So the indication for that is E, and that stands for the German word which means opposite. And so the high groups, highest in priority groups, on opposite sides of the double bonds line, longitudinally. So here's another case. So let's say our priorities come out like this. And so if we look at, again, each carbon separately, this number 2 is higher than 3. And on this end, 1 is higher than 4. So now we've got our highs and lows labeled. Again, we'll look longitudinally. We've got the 2 highs on the same side of the double bond that goes through the center of the double bond. And so this one is like cis, and the thing we use to designate that is Z, and that means the German word together. So let's try that on actual molecules. So here we have one double bond, and this one is drawn with this hydrogen coming down this way, and then we have this chunk of stuff. Well, we have a carbon, a carbon, a carbon, and a hydrogen directly attached to this double bond. Now, one thing you shouldn't lose sight of is that we still have to number the chain and do all of that other stuff. And so we'll do that too. So I'm putting the numbers for the priorities in circles so they won't get mixed up with the numbers for the chain. So this carbon is higher in priority because it's got a bromine on it than these two. And this one is higher because it's got a hydrogen-hydrogen carbon, and this one has hydrogen-hydrogen carbon, but then this one has hydrogen carbon, and this just has hydrogens on it. So this chain is higher in priority than this chain. So that establishes the whole thing. So that puts the 2 highs on the same side, so that's together, that's Z. And so here's our name for that. And you notice that we started numbering from this end and went out to here to get this 7 carbon chain for this guy. And there are 2 styles of nomenclature, either breaking open the word for the placement of the double bond or not. And we put the indicator for whether it's cis or trans or E or Z out in front of the whole name. So let's try it again. On this guy over here, we don't need to do a geometry on this guy because this is a situation where we have the same 2 things on the carbon, kind of like the big molecule we looked at earlier. So there's no geometry argument for that double bond, but this one we do need a geometry argument because we've got a hydrogen and a 2 carbon chain and a methyl, and then we have the rest of the molecules. So we do need to do it. So once we establish our priorities on here, this carbon is the highest priority carbon because this counts as carbon-carbon hydrogen. 3 hydrogens, hydrogen, and this counts as carbon with 2 hydrogens, so there's our priorities. So again, we'll decide that the two highs are on the same side of this double bond, so that's going to be Z again. And we had two double bonds, and so we can either put the numbers here or here to tell where they are. And you notice that when you start drawing this structure, if you just had this name and you started drawing the structure and you didn't know which double bond with the Z, as soon as you start drawing it out, you'll know which one it goes with. Alright, so let's look at this molecule. This time, both double bonds need an E or Z designation. And so we're going to have to establish the priorities, and so I'm going to use different symbols for the priorities around this one as opposed to around this one. So bromine is the highest priority and chlorine is the second highest priority. Because of their atomic numbers, they're going to be higher in priority than the carbons, and so we once again have a Z situation here. So let's do the priorities over here. So we have carbon, 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 carbon. So in order to break the ties, this carbon has on it two carbons and a hydrogen. This one has one carbon and two hydrogens. This one has one carbon and two hydrogens. And this one has three hydrogens. So that was the lowest priority, and this one is the highest priority. Between these two guys, this one is higher because when you go to the next carbon, it's got the chlorine on it. This one just has hydrogens on it. You notice that we never got over here to worrying about the bromine, and we actually got a highest priority before we ever got to the chlorine. So be careful that you don't look further than you actually need to establish your priorities. This time we have the highest priority on opposite sides, so we're going to have this one be an E. And so we know which one is E and which one is Z. Now we need to add a number with the letter for each one so we know which one is which. You can't just put ZE or whatever out here. You have to put the number of the double bond to make it clear. So this one has a fairly lengthy name because of all the stuff that's hanging off of it. But that's how you treat that, and we again have a diene, so we've got that inside of the word here. You can't mix styles of nomenclature, so if you need to use E or Z designation on one double bond where you have several, then you have to use E or Z designations for all of them. In this case, this double bond over here, it would be clear enough if I said cis for this one. But this one, it would not be clear because we wouldn't be absolutely sure what we were talking about because we have the situation where we have three different things and the two things that are the same thing are not on the same carbon. So I can't use cis or trans for that one. So I'm going to have to use the E or Z designation for both of them. And of course cis is like Z. So this one over here is going to be Z, and this one, when you get it figured out, this one's going to also be Z. So there you go. I've got the two numbers and the two letters out in front to show the geometry for both of those double bonds. So these are the two that we started out with when we first realized that we needed to deal with this. So if we go back to this guy, okay, here's your highest priority. We have these two are the lowest priority under this one. But if we look at it, this is high and this is high on either end of this double bond. So this one's going to be Z and this one's going to be E. And if we number the chain and to get the whole name, then we've got our priorities there. And so make sure that you understand what we're talking about here when we do this. And so the full IUPAC name of this guy is Z2-chloro-3-methyl-2-pentene. We know that these aren't the same molecule, and so this one must be E. But it's got all the same numbers. Everything's attached to the same carbons. It's just only different in that third dimension, the geometry question. And so this one is E. 2-chloro-3-methyl-2-pentene. Another kind of question, sometimes you'll see a lot of natural molecules have a lot of double bonds in them. So here's another kind of question that you might have is how many of these double bonds are Z? So you could go through here and you can assign E or Z to each one to answer that question. Or I could ask how many of them are E. And again, you still need to go through and look at each one to determine what they are. This wood doesn't need a designation because you've got the same things on the same carbon. This one could be trans, but that's like E. This one could be like cis, but that's like Z. So those two are pretty easy to do. And so you've got 3 of them done, so now you just have to do these other 2. And if you think about it, this carbon and this carbon are going to be higher in priority than the methyl, so this one's going to be Z. And this one looks a lot like trans, and so that one's kind of one of the ones that's tricky. But you see this group is higher in priority on this end, and this group is higher in priority on this end, so this one is Z. So you have to be careful about that kind of situation. So if we just go back and label, there was one of the easy ones, and that one's Z, that one's Z, Z. Okay. All right, so I'm going to stop this portion for this recording.